started talking about linear homogeneous equations in two variables, so equations of this type, where we have f and g to be functions defined in some domain D and also be continuous in this domain. And today we will continue talking about this equation, and we will just talk more about characteristics and integral surfaces. So here I just drew again our surface. So this is, suppose that we have this equation, right? And we found its solution, an integral curve z equals psi of xy. And this is here, this is our surface. And then we take a plane z equals constants and find the intersection of the plane and the surface. And this is red line, and this would be the level curve. So, and level curve, suppose we can parameterize this curve with parameter t, and so x will be phi1 of t, y will be phi2 of t, and z equals that constant. And our functions are C1, so it means they're continuous and have continuous derivatives. So this is here in red. And we can project this curve onto x or y plane, onto this plane, and we will get a similar curve here, just z will be equal to 0. And so by changing this constant, say from 0 to this value, we will get a cylindrical surface, right, with the base, that is, its base is this curve, and then we'll get this cylindrical surface. And so last time we mentioned that if we, of course, if we compute psi on phi1, phi2, right, on this curve, and this is a level curve, then we will get this, the same constant that we had here in green. And then if we differentiate this equation with respect to t, with respect to our parameter, we will get this, right, derivative with respect to first argument times phi1 with respect to t plus with respect to second argument, which is y, times derivative with respect to t. And also we can rewrite our equation 1 here if we just plug for z our solution psi, right? That will give us psi x times f plus psi y times g. And now let's look at this system, and let's consider this system as system of homogeneous algebraic linear equation with respect to psi x, psi y, right? Since we have psi x, psi y times some coefficient here, and here again we have psi x, psi y times coefficients. So let's look at this system as system of two linear equations. And of course, this system has a trivial solution, right? Since it's a homogeneous system, then and trivial solution we will get when psi x and psi y both equals to 0. And we were talking last time that we are not interested in such a solution because it will be just a constant. So we had an assumption that psi x and psi y are not equal to 0 at the same time, right? So we have this condition. So we want to find a non-trivial solution, and one non-trivial solution system of linear homogeneous equation has one, the rank of the system is less than n, now less than 2. Right, so we can, so basically our coefficients are linearly dependent, so determinant must be 0 then. So we can write this condition if we want to find non-trivial solutions. And this condition obviously holds in the situation if we say that phi1 equals prime equals f and phi2 equals g. And in this case, we will have this system of equations, and we can notice here that those equations, they do not have psi in there, right? So they do not depend on psi. So psi is one of our solutions, and if we take a different solution, say instead of psi we'll take psi1, some different solution to our equation, we will still get the same, and if, right, so we said that this cylindrical surface, so if we have somewhere solution here, the projection would be the same. So we will still get the same equation, and if we look at the plane x or y, if we assume also that our surface is continuously differentiable, is smooth, then if we slightly change c and still in the same surface, right here we will get another curve. So we can see that in these assumptions of continuity through every point in this domain D, so this is a bigger domain D somewhere here where we study our equation, we will have through every point, we will have a certain curve, right? So we'll have a curve, some curve with some phi1 and phi2, right? Such that this equation holds, right? So x prime equals f, y prime equals g. So this is the system we got, and this system is called the system of characteristic equations. Okay, before considering examples, let's just summarize what we said. So these are characteristic equations, right? And x prime equals f, y prime equals g. Characteristic curves are curves, parameterized curves with parameter t. X is phi of t, y is phi2 of t, and z is a constant. So what we have to say that the following properties that we mentioned. So every integral curve is constant on every characteristic, right? So if z equals psi of xy is solution to our equation, then psi evaluated at phi1, phi2 is constant, right? We discussed that. Then, so if we have a characteristic, and if this characteristic has a common point with our integral surface, then the whole characteristic lies in the surface, right? So if characteristic and a surface have one common point, right, then all points of this characteristic belongs to the surface. And the third property that follows from what we discussed, if we have two integral surfaces, right, and if these two integral surfaces have a common point, then they have the whole characteristic that passes through these points in common, right? So then they share a curve. And number 4, so a function psi is a classical solution of our equation 1 if it is continuously differentiable in the domain D, and it is constant along every characteristic curve. And so basically the conclusion is that integrals of our equation 1 are continuously differentiable functions, z equals psi of xy, which are constant on every characteristic in their domain. And here, let's consider a few examples. So first example would be, let's look at the equation AP plus BQ equals 0. So here we use this Monge notations. P is derivative of z with respect to x and Q derivative of z with respect to y. And if A and B are constant, we can see that this equation is basically a linear transport equation. If A is not 0, we divide by A, we will get P plus B over AQ equals 0. So it's linear transport equation. So then characteristic system, this system, right, for this equation will be x prime equals A and y prime equals B. And we can solve, integrate each equation and derivative with respect to t, with respect to our parameter t. So solution to this equation will be at plus a constant. Solution to the second equation will be bt plus a constant. So this is just arbitrary constant of integration. And if we want to eliminate t from these two equations, to have x as a function of y as a function of x, right, then we can express t from here, plug it in here, and then we will get that the y minus ba equals this constant. Right, or alternatively what we can do, if we look at this system and rewrite it and divide one equation by another, so we will have dy dt over dx dt equals b over a, and then what a physicist would say, we will multiply by dt, this fraction, so then we will have dy dx equals ba, and integrating this with respect, so considering y as a function of x and integrating with this equation, we'll get y equals ba of x plus c. B over a, both a constants a and b are given. So if we look at this equation, and I just put here c is this expression if we were solving it just the first way. And you can see here that if we will be changing our constant c, the slope of our line, or we can see this equation of a line, the slope will be constant. So characteristics are parallel lines. Right, so characteristics are parallel in my mind, lines. And so what will be integral surfaces if we think of a set of parallel lines in the x or y, and then to get integral surfaces we have to construct continuously differentiable surfaces such that it's made out of lines whose projections give us some parallel lines. So integral surfaces would be some cylindrical surfaces of, for instance, something like that, made out of lines whose projections give us a family of parallel lines. So the previous example, we considered an equation with constant coefficients. Now let's consider equation with variable coefficients. Right, so we have xp plus yq equals 0. Again, p is derivative with respect to x, q is derivative with respect to y. So here our characteristic equations. In this case, they will be written as x prime equals x and y prime equals y. So let's look at the first equation and recall the undergraduate course of ODE, how to integrate this inseparable equation. So we put dx over x multiplied by dt, then we integrate, it will be ln of absolute value, t plus a constant, then we take exponential function from both parts, we'll have absolute value of x equals e to the t plus this constant, and then we can rewrite, instead of absolute value plus or minus, here e to the a, and this whole thing, it will be some unknown constant. So finally our solution has a form x equals a times e to the t, where a is an arbitrary constant. Right, so, and the equation for y is exactly the same equation, so we will have x equals a e to the t, y equals b e to the t. So this is parametric representation of our characteristic, a and b are arbitrary constant. If we eliminate e of t, for instance, expressing from the first equation, e of t is x over a, we will get that y equals b over ax, and b over a is just some arbitrary constant. So equation we have is y equals cx. Or alternatively, like in the previous example, we can divide one equation by another just to eliminate t from the start, and then we'll have dy dx equals y over x, and similarly we integrate, so then we rewrite it as dy over y equals dy over y equals dx over x, then integrate both parts, we will get, of course, the same answer, right? So y equals cx, and c is now an arbitrary constant, so characteristics, and those lines, they pass through the origin, right, in the x or y plane. So we can think of characteristics as arbitrary rays emanating from the origin, and integrals will be differentiable surfaces that can be built by translation of those rays along the axis. So if we have a domain that includes origin, then we will get solutions like z equal constant, and we will get another type of solutions that are those surfaces called conoids, and I draw here, so if domain D doesn't include the origin, I draw here just one of the conoids. They look like some sorts of skirts, so you can look just in geometry what conoids are. Let's look at another example. So yp minus xq equals 0. Right, it's the same type of example. So we have x prime equals y prime equals negative x. Right, characteristic equations. So to find characteristic curves, let's just divide second by equation by the first. So we'll have dy dx equals negative x over y. Then separating variables, we will have y multiplying by y dy minus x dx, and we will get an equation x squared plus x squared over 2 minus, after integration, y squared over 2 minus x squared over 2 plus c, and so we have that our curves will be x squared plus y squared equals constant. Right, so we have concentric circles centered at the origin. So how we can build our integral curves? By translating this, so basically, so center doesn't change, they all centered at the origin, but the radius of this circle changes. So by translating this circle, we can build integral surfaces, and of course, if we want everything to be continuously differentiable, so we build surfaces in such a way that we don't have vertical tangent plane. So we can get something like this. So we roughly discussed how to find characteristics and integral surfaces. Now let's just get an idea how we can solve a Cauchy problem. So how we can find the unique integral curve that passes through a given a unique integral surface that passes through a given curve. So far I will just state the main ideas, and I will prove the theorems later. I just want you to have kind of a taste what we're doing. Right? So suppose we're given a curve. Right? So this is a curve, and this curve is a parameterized curve. So S is a parameter along this curve, and we want to build an integral. So here I have to write surface. Integral surface is through a given continuous differential curve. Okay, so here is our parameterized curve, and I gave it a name C sub 0. And then this curve can be projected onto X or Y plane, so we will get a projection of this curve. So I call it a projection of C sub 0. And by getting a projection, we will get just Z would be obviously equal 0, so we will have a curve in the plane X or Y, and X is function of S and Y is some given function of S. And then if we want to find unique solution, and then we will see that it exists only if this projection of our curve does not touch characteristics, right? Because our function is constant along characteristics. So you probably can get an idea why we have this condition, and this condition can be written as this equation. So if this is the case, if our characteristics do not touch the initial curve, then so through each point we can draw a characteristic, right? Here, the corresponding characteristic, and then we can build an integral surface. So if you remember, in our notations we had parameterized, our characteristic lines were parameterized, and we used parameter t. So then we can write that our surface that we are building would be depending on two parameters, on parameter t and parameter s. And so here the equation, and you know, if we want to have an equation of a parameterized surface, we do need two parameters, so t and s would be our parameters. Let's consider another example. So solve Cauchy's problem. So we're given an equation and an initial curve. So let the equation be yp plus xq equals 0, and the initial curve parameterized by parameter s, when x is s, y is alpha s, where alpha is any number, any real number not equal to plus or minus 1, and w is just an appropriate, so z equals w, where w is a function of s. And then characteristic equations can be written as x prime equals y, y prime equals s, x. Just we can, by integrating them, for instance, if we just divide one equation by another, and of course we assume right here that f and g, they are not simultaneously 0, so if one of them is 0, we can just switch the division. So for instance, if y is not 0, divide the x, equals x over y, and then we just multiply by y, multiply by x, divide by x, multiply by y, and multiply by dx, and then integrating, we will get that y square minus x square equals a constant. A is a constant, is an arbitrary constant. So how we can find this arbitrary constant? We will use initial conditions. So we know that in the beginning, when t equals 0, our surface that we're trying to build passes through this curve. So at this moment, x equals s and y equals alpha s. So x is s and y equals alpha s. Right? So we plug this into this equation. We'll have alpha s square minus s square, and that must give us an a. So from here we know what a is. This constant a depends on s. And then finally we just plug instead of a this value. So we have our equations y square minus x square equals s square alpha square minus 1. And then we solve this equation for s. Right? So from here s would be plus or minus square root, and plus, of course, corresponds to positive s, values of s, and minus to the negatives. And then by plugging, so just to find our z, right? So we are looking for solution in the form of z equals some function of s and t, and so by plugging this into equation, we'll have w of s, and that will give us our surface.